When studying any programming language, one of the first things you'll learn is what a function is. The syntax is somewhat similar in most programming languages, but have you ever wondered what a function is at a deeper level? At the start of our journey, let's briefly consider the hardware, because all a function can do is interact with the hardware in some way. We will narrow our focus by ignoring many things or simplifying some things, but I'm going to rely on analogy as little as possible. If we imagine a desktop tower, inside the tower we have a CPU and some RAM. We can zoom into the CPU and see a control unit as well as some registers. We can also zoom into the memory and see that it's organized into 4-byte sections. This assumes 32-bit x86 architecture, simply because we need to pick an architecture to focus on. Now, a point of confusion for me was knowing how the hardware was set up and then hearing explanations speak about stack and heap memory. There is nothing physical about stack and heap. Stack and heap actually refer to ways of accessing memory rather than types of memory. The rules are enforced by the operating system and to some degree by the control unit. If you think of programming in terms of controls or robotics, my background, then you need to understand that at a low level, a PC only runs an operating system. Most programmers build on top of the operating system, not the hardware. In almost all programming languages, the core skills or building blocks include the same features. One of those key skills is the function, the focus of this video. In this video, we'll consider a short function written in assembly. You may notice in Visual Studio I am calling the assembly function from a C script, but our focus will be on the function itself. This sample code is from a course on Udemy, so if you like the sample you can check it and other examples out there. Explanations of functions in x86 typically include too much abstraction for me to follow. Basically, our function just interacts with two main types of memory, registers and RAM.
So the top half here is registers, and it's just the registers, and as we go I will just uncomment out the register that changes. So if I didn't uncomment it, it stayed the same value. Like if I didn't write anything in the box, then it stayed the same value that it has on the left hand side. And then in the bottom half here, it's working a little bit different. So what we have will not be, it's not going to be what changes, because during this program we're not actually going to change the stack. Instead, I will highlight the parts of the stack that were relevant to the instruction. So the top half will mean a change, the bottom half will mean that part of the memory was relevant to the instruction. Then the other thing that goes on in the left hand, in the green here, I have the memory addresses. So these are the addresses in memory of these places of the stack. But in the right, I'm not going to include the memory. Instead, I'll include the value that's in the memory. It'll be the value that's relevant. So that's what's going on there. So let's get to our first instruction, which is adder ASM proc. And when we do that, everything you see in this column is the values that we have when we first run this first initial instruction. So the next instruction, kind of our first actual instruction in the program, we push EBP. So when we push EBP, what happens is we increment the instruction pointer. I probably won't point that out again because the instruction pointer will increment every single time. But the other thing that we do is you'll see when we pushed EBP, ESP changes. So ESP did have this value, which is a value that points to an address in memory, which has actually this value right here. You'll notice they're the same. Or sorry, ESP. Yeah, ESP did have the value that is going to be inside of our stack that's relevant to this function. Before we did anything, ESP had this memory address stored. After we push EBP, the new address that is stored in ESP is this memory address right here. And then, yeah, that's pretty much it. So that's why here I wrote, this was the place in the stack that was relevant, and I just wrote the contents of the stack instead of the memory address where those contents are located. So our next instruction is to move ESP and EBP. Let's see what happens when we do that. Oops. So when we do that, we'll see that EBP gets the same value that ESP had, which is this memory address, for the stack. And down here I just put an ESP because EBP and ESP are both have this same address now. When we do our next step, it'll be move EBP plus 8 into EAX. So when we do that, we get, we're moving something into EAX. It is the value 1, 1. That something was inside of this EBP plus 8. So it is this, EBP plus 8 stands for this memory address, and the contents that were already inside of, again, these at the bottom are not changing. I just did not reveal in the beginning what the contents were. The contents are already here when our function is called. I'm just revealing them as we go. So I'm now revealing that inside of this memory address we had the value 1, 1, and this instruction is moving that value from this address 1, 1 into EAX. When we see our next instruction, we'll see that we're doing EBP plus 16. So EBP plus 16 stands for this address. The value that was already inside of that address, I'm just now revealing it, was B. And we're moving that B value into EDX. And you'll notice that that is ABC is what we're doing. So this was A. This was the variable name B. And then this one's going to be our variable name C. So the next one, when we do EBP plus 16, that's going to take this address, which is what EBP plus 16 stands for, and we're going to move the value from that address into EDX. And when we do that, bam, there it is. E is what was already there. Again, I just now revealed it, but it was already there from the beginning. And we're going to move that into EDX and increment the pointer. The next thing we're going to do is an add instruction, and again, EAX, ECX, that's EAX, ECX, we're going to add those together and we're going to store the result in EAX. And this was, again, using the variable names that we passed in from the C program. This is A, B, C. But when we add in assembly, we can only add 2 numbers. We can't add all 3, so we have to add 2 and then add the third one to the result afterwards. So that's what's going on here, is that first step, we're going to take ECX plus EAX, so 1, 1 plus B. We're going to store that result in EAX, which is 1C. And this instruction, this add instruction, also changed EFL and a couple of the flags. We're going to do the next add instruction, where we're going to add EDX, which represents our C variable. And we're going to add that to the sum that we just produced. We're going to store that result in EAX, which will give us 2A. 2A is now our final value for our sum. So this is what we want to return from our function, and this is where the return value needs to be in EAX. So that's good. Now we just need to clean up the rest of the function. So we'll pop EBP, and when we pop EBP, you'll see that it returns ESP returns to the value that it had when we initially called this function, and at the same time EBP also returns to the original value it had when we first called this function. So that's what we needed. And then we also needed, so ESI, EDI, we didn't ever mess with those, so we didn't have to do anything to fix them because we never messed with them. So EDI we never changed, ESI we never changed, and EBX we never changed as well. So that's why we didn't have to do anything with those. Then our last step here is to return. And when we return, you'll see that it changes the value of ESP again, because now when we return, we're returning back to the C function that called us.